we go to our next plenary lecture, and if I can see, it's will be presented from the group of scientists from our host country, from Crete. And do we have this person who will be presenting?
It's Professor Nikolozakis, and he's here. He can open his camera if you want.
Because I do not
microphone.
see. Okay.
Yes.
Okay, so the next plenary lecture is from Department Forensic Sciences and Toxicology Faculty of Medicine, University of Crete. And it will be presented by Dr. Professor Petrakis on behalf of Nikolozakis, Petrakis, and Tsatsakis. And I know personally Professor Tsatsakis, and I'm glad that we will hear today this lecture about toxicology issues related to COVID-19 outbreak, kinetics and the dynamics of COVID-19 diagnosis and potential treatment. Please, could you please share screen that we can see the presentation now?
We have Professor Nikolozakis. If he can unmute his microphone so we can hear him too. He's online, he's connected, and I can see his camera.
Professor Nikolozakis, are you here? Because I see the empty picture and no microphone.
Yeah.
So the person is not here, I think.
Let's give him a moment. I will try.
Yeah, could you please?
Yes, yes.
Do we have any advertisement or whatever information? Is Professor Stillman still here with us? Okay, we just wait a little bit.
I am here.
Миша, у нас все лекции сегодняшние или кого-то нет?
Ну, я не знаю, я считал, что все.
Окей, я буду объявлять. Хорошо, спасибо, Миша.
Надо посмотреть сейчас, я посмотрю внимательно.
Спасибо. Ну, у нас в любом случае после этой лекции небольшой перерыв, а потом уже следующий.
А это-то будет?
Ну вот Альбина стала выяснять сейчас.
Yanis is trying to assist Professor Nikolozakis to establish a connection and be able to talk to us. Okay, so we need like 2 minutes.
So are we waiting or we just make a small break or whatever?
We can wait 1 minute, I think.
Okay.
Because he's on the phone with Yanis. So
Okay, we will be waiting.
Connected. Okay, I'm sorry. Maybe he has a bad internet connection. I'm not sure.
Yeah, okay, we can wait till he can try again.
Oh, and Professor Tsatsakis is now active here.
Oh, okay. Professor Nikolozakis, are you here now?
Hello?
Could you please switch on microphone? Okay.
Hello, can you hear us?
Can you hear?
Where is Professor Tsatsakis?
Professor Tsatsakis here, but we are waiting for Professor Nikolozakis.
Hello, can you hear us?
Natalia?
Yes.
Okay. Please proceed to the next lecture. Then we have a
break, yeah.
We have a break if you want.
So let's...
what we're supposed to do?
Yes?
There is a problem with the connection. for Dr. Nikolouzakis?
I am not sure. We can see him.
We can see him, but not he.
But I don't see him also. For me, I don't see.
I see him, but I cannot hear.
Professor Nikolouzakis, are you hearing us? Are you listening? Hello?
Okay, I see him now. Okay. It's recording. Hello?
Он не может подсоединиться?
No.
No, he is here, but not with microphone, or something is not working with microphone.
Can you try to share your screen, Professor Nikolouzakis?
I'm afraid he's...
Okay.
Oh, great.
Yes,
Great.
He started his presentation, but...
Yeah, but we need the voice.
We need, yes.
To activate the microphone. Okay, he's preparing.
Microphone? Okay.
Yeah, I saw him connecting. Professor, would you like to start? Can you hear us?
I think he's speaking, but he's showing that something that we cannot hear him.
Okay, give me a moment.
В чем у него сложности-то?
То ли микрофон не работает, то ли неправильно работает, непонятно.
I'm sorry. Professor Nikolouzakis, I see that your microphone is connected and your camera, but we cannot hear you when you speak. And I don't know if you can hear us. Do you have a microphone connected? You can hear us, but we can't hear you. Okay. Let's see. I can somehow from Zoom platform assist with your microphone, but please go at the mute button and click the arrow and see audio settings. If there is an option that says select a microphone, you have to click microphone.
А пусть он включит его.
First option.
Вот сейчас включил. Должно быть слышно его, потому что он включил микрофон.
Но мы не слышим. Нет.
We are really sorry.
We are not.
Mr. Nikolouzakis, he is currently on duty at the hospital, and he is using his computer from the hospital, so he has some technical difficulties. Would you like to go on a break for some minutes, or
maybe we can continue, or
yeah, if you wish to, if Professor Zubov is ready, and we can switch.
Natalia.
Yes.
As I said, please proceed to the next lecture without a break.
Okay.
And then until that time, probably he is okay, or we proceed with the next lectures and he will be at the end.
Okay.
Please proceed to the next
let's proceed to the next lecture. If Professor Zubov is still with us.
Here. I'm still with you.
Okay. So our
The
next
spectator now will be speaker.
Yes, our next speaker is Professor Zubov, again from the group of scientists, Shemyakin-Ovchinnikov Institute of Bioorganic Chemistry, and the National Research Center, Kurchatov Institute, and the Prokhorov General Physics Institute. And the title of the talk is a little bit different from the program. So it's tetramer of aniline as a structural analog polyaniline, the material of biomedical and electrophysical application. Could you please proceed, Professor Zubov?
Yeah. Thank you very much, Natasha. And let me first say hello to all the colleagues, participants. I'm quite happy with all our team to participate in this conference, although it will be better to make a direct participation, but nevertheless, this online participation is also quite good. So I will talk today about the tetramer of aniline, the structural analog of polyaniline. And the reason for that polyaniline is a very popular material, cheap, easily available, with many, many interesting properties studied by conductivity, so it's organic semiconductor, chemical stability, various reactions, biocompatibility, and bioseparating behavior, which I will talk about later. But at the same time, and the formula, of course, is here on the top, and at the same time, it's not a very easy object. It's usually obtained as a thin or nano-thin films deposited by direct chemical synthesis in situ of polyaniline, which makes it not very reproducible, with ill-defined structure, sometimes with many chemical and morphological defects, and very poorly soluble. So there is a temptation to use his low molecular weight analogs with similar electronic structure. There are a number of known oligomers of aniline, and to our opinion, the most attractive is tetraaniline with phenyl groups at both ends. The advantage of this material, first of all, is again rather easy availability, well-characterized molecular structure, so it's individual compound, good flexibility, but the question is how this short piece of the long polyaniline chain can represent the main attractive properties of the high molecular weight polymer. What we know at the beginning that it's possible to have, like polyaniline, this analog in three forms: emeraldine, and pergranulin, both in the basic form and in salt, similar to polyaniline, which is not shown on the picture. So the first task was to synthesize this molecule, to characterize it carefully, to prove that it's an individual molecule, and then study some properties. So the synthesis was done according to the literature, and this is one-stage coupling reaction, and we did it, isolated and purified the material, and then structure, and also by simple oxidation reaction, we produced another oxidation form, which is called by abbreviation tiny EB. Now, first question to see how it is in individual compounds and not a mixture of various products, various oligomers, and that's mass spectra of those compounds, both in the leucomeridine base form and in the emeridine form. One can see that those are very pure single molecules, with calculated and determined molecular weights exactly corresponding to that expected material. Now the infrared spectra, again, they show that after analyzing the peaks, they all correspond to the groups and bonds represented in that formula. The same relates to the emeraldine base, and further, we recorded and analyzed for the first time the NMR spectra, the proton NMR spectrum, and C13 NMR spectrum, and they all show that the structure really corresponds to the compound which was synthesized. The same relates to the tiny EB compound, proton NMR spectrum and C13 NMR spectrum, both correspond to this structure. Now, we may start to come to the next point of our program, to see if we'll manage to develop technology to make nano-thick uniform coatings, to modify various supports, to make functional materials with a functional layer of aniline tetramer, which by itself, of course, is not possible to use as a material, because it's a low molecular weight solid powder. And in comparison, we show how it works with a high molecular weight polyaniline. So those are scanning probe microscopy images of polyaniline material surface on the glass plate support. We can see that this chemical precipitation polymerization, chemical deposition of the layer produces rather smooth and continuous with no defects film, which made it possible to use these materials for many application directions. But despite of the good solubility of these low molecular weight analog, our attempts to make good films by using traditional deposition film techniques like solvent evaporation from the solution, slide B, and spin coating from solution, slide C, didn't produce good continuous non-defect materials, bumpy with holes, so those are not really possible for use as a functional matrices for further testing. So in order to make a reliable technology, we applied the Langmuir-Blodgett technique to use monolayers and the Langmuir bath to deposit solutions of aniline in various solvents on the water surface and move the barrier, and then pick up the materials on various stages, on various surface pressures. Oh, something happened to my picture.
Something happened to the presentation. Альбина?
Это этот Николазова включил свой просмотр экрана. А вы не закончили еще?
Нет, конечно.
Нет, еще.
Зачем? А это он зачем-то включил просмотр своего экрана, господин Николазовас. И вот, сейчас мы продолжим. На каком слайде остановились? На каком слайде?
Я не помню порядок.
Сейчас. Вот, все, продолжайте.
Yeah. So, it was found that in different solvents we have surface pressure area diagrams, very typically looking for the normal Langmuir films or surfactants on the surface. But surprisingly, the surface area per molecule or apparent surface area per molecule drastically depended on the nature of the solvent. So the minimal surface was casting from toluene, the middle is the methyl sulfoxide, and the right is a mixture of toluene and dimethyl sulfoxide for the same molecule. We thought that it may be, the origin may be that we have in different solvents not a homogeneous molecular solution, but some kind of a aggregated colloidal solution, and the behavior of those aggregates on the surface results in formation of the multi-layer structures, bumps and islands, which make the picture quite different from the expected monomolecular film. So in order to check this, we started roof triangle photographs of the surface Langmuir layers, and the upper line is toluene, middle line is dimethyl sulfoxide, and their mixture is a lower line, where we have the minimal surface area per molecule. One can see that in both cases we have very aggregated, very rough structure with bumps and islands and something in between them, and very uniform layer, which is a good basis for further experiments. For that, we did surface pick up from the surface by the Langmuir-Schaefer technique, and in fact, if we did it from the toluene, we have again islands and very uniform layers deposited on the solid supports, one layer, two layers. Instead, toluene dimethyl sulfoxide mixture produces much more uniform films with small aggregates, not tall, and no surface holes. So this is a good basis for further testing of the tetramer as an analog of polyaniline. For that purpose, we decided to study, first of all, bioabsorption behavior of tetramer as compared to the polyaniline, to biomolecules, nucleic acids and proteins, because, as I show you later, it was shown that polyaniline shows the unique property of zero serotonin activity to nucleic acids, especially double-strand DNA, somewhat stronger binding for RNA, and strong bind of proteins, of humic acids, of chlorophyll, hemoglobin, and so forth. Well, the technique we used for that was so-called spectral correlation interferometry, first developed by the group of Russian scientists. And the essence of the technique was interference of the reference beam on the glass plate with deposited reference layer, and when something is adsorbed on that surface, the interference picture is changed, so one can treat this with the developed technology and show the kinetics of absorption thickness of adsorbed layer, kinetics of desorption, and many other features in the nanoscale real-time mode. So for that purpose, we use several biopolymers, double-strand DNA from the E. coli, and several proteins differing with molecular weight and PI values, starting from the high to the low PI. The results are shown on this slide. On the left-hand side, there is a results of sorption study of various nucleic acids and proteins on the polyaniline surface produced by the nanothick layer deposition on the polyaniline on the glass slide. And one can see that nucleic acid is completely not sorbed. Most of the proteins are quickly adsorbed on this surface. They reach equilibrium. Sorption capacity is limited. And when we changed from protein solution to buffer PBS solution, the same pH, they remain. And then finally, when we change pH, they gradually elute from the sorbent. On the left-hand side, is similar study of nucleic acid and different proteins for the tetramer. And one can see that after introduction of protein solution, adsorption of protein starts, nucleic acid is not adsorbed at all, and adsorption layer remains when protein solution is changed to the PBS buffer, and again, reversible desorption from that layer when changing pH. So it means that sorption behavior of those two materials, although a great difference in molecular weight due to the chemical similarity and similar electronic properties, are quite similar, so we can use in many applications tetramer for creating of biosensors, biosorbing elements, and for other biotechnological purposes. Now, a few words about the electrophysical properties of tanning. For that, it was necessary to dope, and we doped this with the toluene sulfonic acid, produce the salt, and then the device to test electrophysical properties looked as follows on the lower part of the picture. And for testing, we decided to use composites of doped tetraaniline with nanocrystalline silicon, which is semiconductor. So this is a use of a organic, probable, expectable semiconductor with inorganic, and we tested that on the device, which looks like a condenser or capacitor with two electrodes, so we can measure its property as a capacitor and electric conductivity on various frequencies in the wide frequency range. Here the impedance spectra, real and imaginary dielectric constant of nanosilicon films, 1 and 1 prime, and composites, tiny EB, toluene sulfonic acids, curves 2 and 2 prime. I draw your attention that the curve 2 prime shows the real component at the zero and at zero frequency. It means under the conditions of capacitor. The value of the module, the capacity, is several times higher. In terms of the condenser, it means more than 50 times more capacity, because it is directly proportional to the epsilon prime value. So I may note that it's impossible to prepare similar composite from the high molecular weight polyaniline. And here the advantage that easy solubility of tetramer allows to make the molecularly or colloidally mixed homogeneous mixture with nanosilicon. And the last slide shows the conductivity of the high frequency range, and curve 2 is a composite, and we can see that the conductivity in the high frequencies of this composite becomes 1 order of magnitude higher than just simple semiconductor. I think I finished on that, and my last slide is thank you very much for your attention.
Thank you. Thank you very much, Professor Zubov, Vitaly. I apologize, but I was asked to go directly to the Professor Nicholas Zakis. Okay.
Please go.
Questions?
Yes, go with the questions.
Okay. So
Zubov, and then proceed with the next, and we shall have this one at the end. So
okay.
Do as it is.
Okay. So everything is changing every minute. So questions, please. Dear participants, if you have questions, could you please just switch on microphone? Вопросы. Есть у кого-то вопросы? Questions, please. Proceed. No questions.
No, не обязательно, чтобы были вопросы.
Thank you very much for your very interesting presentation.